So this video is all about very, very tiny concentrations. We'll be using parts per million and parts per billion to describe those. So how do you talk about something that has a really, really small concentration? Like if you're talking about the amount of lead dissolved in drinking water, well, hopefully that's not very much, right? Because even tiny, tiny amounts of lead in drinking water are dangerous. Um, so to describe those in a way with numbers that make sense and aren't like super crazy tiny numbers, what we're going to use is parts per million or parts per billion, which literally means how many parts in a million is this very tiny concentration of solute. So ppm stands for parts per million, ppb stands for parts per billion, and the formula is actually really similar to your mass percent formula, but multiplied by a million for parts per million and multiplied by a billion for parts per billion instead. So ppm, parts per million, is going to be the mass of your solute divided by the mass of your whole solution multiplied by a million. 10 to the 6 is a million. ppb is going to be the mass of the solute divided by the mass of the solution multiplied by 10 to the 9, which is a billion. Notice here, so the symbol for parts per million that we're using is going to be ppm. The unit is also ppm. The symbol for parts per billion is ppb. The unit is also ppb. It's kind of one of those weird cases where the unit and the symbol, we're going to use the same thing for those. Now, just to give you a sense of how big is a million and how small is one part in a million seconds, let's convert a million seconds to days, and then we can get a sense of that scale. So if I start with a million seconds is 10 to the 6 seconds. If I want to convert this to days, the first thing I do is multiply by a fraction that equals 1 that will cancel out my seconds. So if I put 1 minute over 60 seconds, the seconds will cancel. There we go. And the seconds will cancel and I'll be left with minutes. Now I need to cancel minutes. So if I put 1 hour, which is equal to 60 minutes, as my next fraction, then I can cancel out minutes. Now I want to cancel hours. There's 24 hours in one day, so I'll multiply by 24 hours per day. Now I can cancel out hours. All right, toss that into your calculator. So we'll do 10 to the 6, which is a million seconds, multiplied by 1 minute over 60 seconds, multiplied by 1 over 60, multiplied by 1 over 24. And what I get is 11.6, and the only unit that I have left here is days, right? So that's the unit that I put here, days. All right, let's think about what this means. So if 1 million seconds is 11.6 days, then 1 part per million, one way you can think about it, is it's about the size of 1 second out of 11.6 days worth of seconds. Right, there are 2 more activities there on your page. I'll have you stop the video here, try those 2 activities to get a sense of the size of parts per billion, and then come back into the video. All right, let's try an example problem with this. So let's say you have a fish and your fish is 1.6 kilograms of salmon, and you find out that that whole salmon contains 0.6 milligrams of mercury. So if you look up Health Canada's recommendation for maximum mercury content in fish, it's 0.5 parts per million. So this is one of those things where it's such a tiny concentration, right? You want to have very tiny concentrations of mercury, or none at all, obviously, ideally. And so because it's such a small concentration, we use parts per million in Health Canada. So is this fish actually safe to eat? Does it come in under that 0.5 parts per million recommendation? Well, let's look at all of our given information here. I know the maximum part per million I can get is that 0.5 parts per million. That's not actually going to come into my calculation. I'm just going to compare to that at the end. Sorry about my voice. I sound like I'm dying. I'm not. I'm okay. Sorry about that. Next, we have that 1.6 kilogram salmon. So that, I know it sounds funny to talk about a salmon as a solution, but that 1.6 kilograms is the mass of the whole thing. When we talk about the solution, we're always talking about the mass of the whole thing. So in this case, the whole thing is a salmon. So my mass of the solution is that 1.6 kilogram salmon. Now, kilograms is the wrong unit. I need to get everything into grams. So the first move I need to do is convert that kilograms to grams, and I do that by multiplying by 1,000 grams in 1 kilogram. That gives me 1,600 grams. Next, I have this 0.6 milligrams. That's of your solute. So your solute is that thing that you have a tiny bit mixed into your whole solution. And that tiny bit is of mercury. So the mass of my solute is the mass of mercury, which is 0.6 milligrams. Once again, wrong unit. I've got to convert that into grams. So I'll just show you how to do that one. So to get milligrams into grams, I'm going to multiply by, there is in 1 gram, sorry, I'm writing with my cursor, it's tricky, there's 1,000 milligrams. All right, so that would cancel my units of milligrams, and I'd be left with units of grams if I divide by 1,000, if I do times 1 over 1,000. Okay, so my formula for parts per million is just the mass of the solute over the mass of the solution times 10 to the 6. So we're going to figure out what is the actual parts per million of this fish, and then we'll compare it to the maximum parts per million recommended by Health Canada. We'll start by just tossing our numbers in here. So the mass of the solute, 0.0006 grams. The mass of the solution, 1,600 grams, times 10 to the 6. Put that all in your calculator. We actually have very few significant figures here, right? There's actually only one sig fig in my mass of the solute. So I'm going to round that off to 0.4 parts per million. So is this fish safe to eat? Well, basically what we've got to do is compare 0.4 part per million to 0.5 part per million. Is it less? It is less, so this fish can hit the market. So that fish would be considered safe. Now there'd be certain situations where you might want to eat a little bit less fish. So mercury tends to build up in fish, it bioaccumulates there. So if someone was pregnant, they might not want to eat fish every single day because that parts per million can sort of start to add up if you're eating a lot of fish. But this fish in general would be safe for the average person to eat. All right, last example. So one standard, and there's actually a few different ones here. Some organizations actually recommend just 0 parts per million of lead or parts per billion of lead in drinking water. But one standard for safe drinking water is a concentration of lead that's less than 15 part per billion. So let's say you have 0.800 grams of lead that you accidentally leach into your water supply. How much water then do you need to have to dilute that little tiny bit of lead? 0.8 grams is not very much. We're going to find out that because the concentration of lead in drinking water needs to be so low in order to be safe, we actually need a ton of water to dilute just a tiny, tiny bit of lead in order to make it within what's considered a safe range. Okay, let's write down our given here. We know that 15 parts per billion, that's the concentration we're going for here. So we're trying to get down to a concentration of 15 parts per billion. We also know the mass of the solute, so the mass of the lead that has leached into our water supply is 0.800 grams. So the mass of the solute is going to be the mass of that tiny thing dissolved. The required thing that we're trying to find is how much water I need. That's really looking at how much solution is there going to be at the end of the day. So how much water do I need to have, do I need to use to dilute that tiny bit of solute? Here's our formula, so parts per billion. Now this is a tough one because we're going to be rearranging for the mass of the solution, right, which is on the bottom. So my first move would just be to divide both sides by 10 to the 9. So just get rid of that 10 to the 9 on this side by dividing this side by 10 to the 9. And dividing this side by billion as well. Oh, that's a 10. This is why I used a text to edit this. So parts per billion divided by 10 to the 9. That will give me mass of my solute over my mass of my solution. The 10 to the 9 on this side cancels. Okay, the problem is here I'm trying to rearrange for something on the denominator. That's no fun at all. So my next move is actually just going to be to swap the numerator and the denominator of both fractions. So this is a math move you can do. It only works if you have a single fraction on the left of your equal sign and a single fraction on the right of your equal sign. But it's allowed if you have that case. And it is useful when you're trying to rearrange for the denominator, right? I'm trying to rearrange for the mass of the solution. So I'll do that move. 10 to the 9 pops on top, parts per billion on bottom. Mass of the solution pops up on top, and the mass of the solute is now on the bottom. Now I'm almost there. I need to get rid of that mass of the solute on the bottom, so I'm going to multiply both sides by mass of the solute. That'll cancel my mass of the solute here. There it goes. And I'll just write it forwards. So the mass of my solution is equal to 10 to the 9 divided by the parts per billion that I've got, multiplied by my mass of the solute. Now you toss in all your numbers. So 10 to the 9 divided by the parts per billion, that's the concentration I'm going for, which is 15 parts per billion. The mass of the solute is the mass of the lead that's leached in, which is 0.800 grams. We put that all in, and we will get a mass of water. In my calculator, let me see what I get. So 10 to the 9 divided by 15 times 0.8. So I get a mass of 5.3. It looks like I can have two sig figs here. So 5.3 times 10 to the, it's a very big number. I've got 10 to the 7. And that'll be in grams. So technically that is actually the mass of the entire solution, which is the mass of the water plus the mass of the lead. But of course, in terms of significant figures, if we are subtracting out that mass of lead, which is only 0.8 grams, that's not going to change my number at all. So for parts per billion questions, the mass of the solution is essentially the mass of the water here. And that is it for this lesson.